Hey folks, welcome back. In this video we're going to look at stars and spectra, so let's get into it. So firstly for stars, it says that stars produce light of different wavelengths depending on their temperature and the elements present. And in the pictures here you can see some different colours of stars, and that's not always apparent when you look up into the night sky, because what you'll often tend to see is just white twinkling lights. But the Hubble Space Telescope was able to produce this picture on the left where you can actually see the different colours. And you've also got some nice different colours shown on the right hand side as well. We've got some blues, greens, yellows and purples and so on. It then says that the colour of a star indicates its temperature. So we say that red stars are actually the coolest stars and blue stars are the hottest stars. So if you go from red stars to orange, yellow, white to blue stars, you notice that these are increasing in temperature. And you might think this is a bit strange to associate the coolest stars with the colour red and the hottest stars with the colour blue, because it tends to be the opposite when we think about temperatures in everyday life. So although we often associate cold things with the colour blue and hot things with the colour red, it's actually the other way about for stars. Moving on, we'll now look at spectra. So it starts by saying that light from a star can be analysed using a prism or spectroscope. White light is split into a continuous spectrum of different colours using a prism. So if you have a look at the picture here, you've probably seen this experiment before in your BGE classes, like in first, second or third year, where you've got white light being split up by a glass prism into the different colours of the rainbow. And this is what we call a continuous spectrum because we get all of the colours of the visible spectrum produced. And I'll just show you a quick simulation to help you visualise this. So if you have a look at the simulation here, we've got a ray box which can shine white light on our triangular glass prism, and then we've just got a white screen at the side to see the result. So if I turn on the light from the ray box, you'll see the white light is emitted and it hits the triangular glass prism, and then this is split into the different colours of the rainbow, where red is refracted the least and violet is refracted the most. Now that was a continuous spectrum that we just looked at, but we also have something called a line spectrum, or if we're talking about more than one, we would say line spectra. So it says here that line spectra contain only some colours, and we've got two types. We've got a line absorption spectrum and a line emission spectrum. So firstly it says that a line absorption spectrum consists of a complete or continuous spectrum with certain colours missing which appear as black lines in the spectrum. And here's an example for you. So we've got the red light going to the violet light for the full continuous spectrum, but then particular wavelengths or frequencies of light have been removed, and at those points we've just got a black band. On the other hand, our second type of line spectrum is called a line emission spectrum, and it says that a line emission spectrum consists of lines of light of distinct colours rather than a continuous spectrum. For example, it might look something like this. So we've now got a black band instead of the continuous spectrum. And instead of just black lines on the continuous spectrum, like we did for the line absorption spectrum, we've now got a black band with colours shown at particular wavelengths or frequencies. So we've got this red line here, this sort of cyan coloured line here. We've then got a blue line which is quite faint and quite hard to see there, and then a violet line. And it says that every element produces a unique line spectrum. So I'll just show you a quick simulation to help you visualise that. So if we look at hydrogen to begin with, there's its unique line spectrum where we've got some more prominent lines like this red one here and this blue one over here. If we look at helium, it's different because it's got this yellow line which is more prominent here and some more blue lines there. If we then go to oxygen, you'll see lots more distinct lines there. If we then go to carbon, we've got even brighter lines for that one. And lastly, nitrogen, which looks different again. So because every element has its own unique line spectrum, studying line spectra allows the elements present in a light source, for example a star, to be identified. This can help to identify the type, distance, age or speed of a star. So this is why astronomers look at spectra. We're able to work out lots of properties about stars by finding out the elements that are present in the stars. And lastly, we have an example here. So it says you may be given various line emission spectra for different elements and asked to determine whether the elements are present in a star or unknown sample. If an element is present in the star, it will have lines in its spectrum which match those of the star. So if we look at the picture here, we've got the star's spectrum at the top, which is the one we want to refer back to each time. We've then got the spectra for different elements below it. So what you would want to do is look at each of these spectra in turn and see if all of the lines in each of the elements here match up with those in the star. And it says the simplest way to see if the lines match is to use a ruler. Now you don't have to do that, but it does help to be able to match up the lines. So for sodium, first of all, you can see we've got a line here which doesn't appear in the star. We've then got these two which again don't appear in the star. Neither does this one, or this one, so we can safely say that sodium is not present in our star. If we move down to mercury this time though, you'll see we've got these two dark lines here which match up with the two up here in the star. We've then got this one which matches with this one which matches with this one, and lastly this one matches up with this one. So because all of the lines in the mercury spectrum match up with those in the star spectrum, that means I can say that mercury is present in the star. And lastly for helium, we've got this line matches up with this one, this line matches up with this one on the left, this one with this one, this one with this one, and then we've got these three lines where we've got a darker one and then two fainter ones on the right, and that's the same as this pattern here, the darker one with the two fainter ones. So because all of the lines in the helium spectrum match up with those in the star spectrum, again I can say that helium is also present in my star. So we can conclude here that in this case, Mercury and helium both have lines which match those of the star, so these two elements are present in the star. And we'll practice doing this in the worked example video for stars and spectra. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.